Hello physics students, and today we're going to look at the force of friction. Friction is a force that opposes the applied force. We're going to look at what friction is, what static friction and kinetic friction are. We're going to look at what friction is on a microscopic level. We're going to look at friction and the normal force, and we're going to talk about coefficients of friction. So let's look at a particular type of friction. Friction in general opposes the applied force. Let's look at static friction. You've all heard static friction, the term used, and we designate that with the capital F for force and a subscript S for static friction. Static friction is the resistive force that keeps an object from moving. So if we have this block sitting on a desktop here, and we exert a small force to push the block this way, static friction is opposing it in this direction and keeps the block from moving initially. Once we apply a larger force, we still have that static friction opposing this motion, but our force is large enough in this direction to cause the block to move. In the case of this second block, our pushing force has overcome the force of the static friction. Static friction, so just to keep in your mind, keeps the object from moving. So as long as our object does not move, the force of static friction is equal to negative of the applied force. So whatever our applied force is, the force of static friction will be exactly equal and opposite to the static friction. So this diagram doesn't exactly show that. It shows the static friction as being a larger force. Indeed, these would be equal and opposite in direction as long as the object does not move. So if we apply this small force and the object does not move, whatever the force is, the magnitude of that, our force of static friction will be equal and opposite in direction, equal in magnitude, opposite in direction. We can continue to increase that small force, a little bit more, more newtons pushing this box to the right. That static friction will increase just as our force increases, as long as the object does not move. When our applied force is as great as it can be without the object moving, then we say that the force of static friction has reached its maximum value, and we designate that the force of static friction max in subscript, S, comma, max in subscript. That means the force of static friction has reached its maximum value, and the object still is not moving. Obviously, if we increase the applied force just a little bit more than that, we have a different kind of friction we're going to be talking about. So when our applied force exceeds the maximum static friction, the force of maximum static friction, the object begins to move. Just as soon as that applied force exceeds our maximum static friction. Keep in mind that there will still be a frictional component as this object moves. That's going to be kinetic friction. Kinetic friction is the frictional force on an object in motion. So that is what the kinetic friction is, and it is smaller than our force, our maximum force of static friction. We can now look at our net external force, at least in this diagram, in the horizontal direction, as equal to the applied force minus the force of kinetic friction. So let's take a look at what is going on a microscopic level when we talk about friction, because that is really where friction comes from. The fact that surfaces are only making contact in a few places as they touch, because even very smooth surfaces are rough on a microscopic level. So this appearance of a steel surface, it might be very smooth, and you might think, wow, it must be just perfectly smooth. But when you look through a high-powered microscope, here's a scanning electron microscope image of a stainless steel surface. that you think is smooth, but look, it's very rough in actually microscopically when you look at the surface. When surfaces are stationary, adhesion caused by the electrostatic forces between the molecules prevents movement. And because of that adhesion on this microscopic level, the force required to cause a stationary object to move is actually, or usually, greater than the force required to keep that object moving at a constant speed. So it has to overcome that adhesion. The applied force must overcome that. So that force of static friction tends to be higher than the force required to keep the object moving. So also the force of friction is very much proportional to the normal force. And here just on a microscopic level, we're looking at a small normal force and a large normal force, and you can see what happens to the surfaces of each of these. When you have a larger normal force, those surfaces are pushed closer together, and the force of friction is going to be greater. And you know that if you're going to try and move this heavy object and this lighter object, the applied force in either case is going to be greater than to move them. You're going to have an applied force that is greater than your force of static friction so that you can overcome the force of static friction. But the force of kinetic friction to move the bookcase, when you're moving the bookcase, the kinetic friction between the bookcase and the floor is going to be greater than the kinetic friction between the chair and the floor. Also, the normal force for the bookcase, that heavy bookcase, is going to be greater than the normal force for that lighter chair. So the force of friction is going to always be proportional to the normal force. So when we think about friction, we know that it is a very complex combination of different forces and at a microscopic level. Friction depends on so many different factors. It depends on the surface itself. Is the surface a rough surface, a smooth surface? How much surface area is there? Different conditions will affect the frictional forces. Are we on an incline? Is there moisture involved? Snow, rain, different things like that. Mud, is it slippery? What's the heat content? How warm are the surfaces? So when we're talking about the relationships between the normal force and the force of friction, we are simply talking about an approximation of friction during dry conditions on a flat surface at rest or sliding past each other. And so that is generally what we're talking about. We're not taking into account all these other factors. Now let's take a look at something called the coefficient of friction. And we get to use this cute little Greek letter called mu. It starts low and comes up. It's a little bit like a U, but it has a long leading edge here. And it goes down lower. Mu. The coefficient of friction is a quantity that expresses how frictional forces depend on a particular contact surface. And the definition of it is simply the ratio of friction to the normal force acting between two objects. We have two different kinds of coefficient of friction that we're going to look at. We're going to look at the coefficient of kinetic friction. So in that case, we're going to talk about mu sub k, a little subscript k, tells us the coefficient of kinetic friction, and that's going to compare the force of kinetic friction to the normal force. And of course, the kinetic friction is when an object is sliding. The two objects are sliding past each other. The coefficient of static friction will be mu with a subscript s, and that's going to compare the maximum static friction to the normal force. And here, the maximum static friction is when an object is still stationary just before it begins to move. How much force is needed to be applied just before it begins to be in motion. So here are some examples of different materials that when they are sliding past each other, these are their coefficients of friction. Their coefficients of kinetic friction for when they're sliding past each other, and the coefficient of static friction. because the force of kinetic friction is generally less than or perhaps equal to the maximum static friction force that would be applied, the coefficient of kinetic friction is going to be lower than or less than or equal to the coefficient of static friction. So you can see that here, the coefficient of kinetic friction is generally lower than the coefficient of static friction here in these for these different surfaces. So let's look at an example and just work through one of these together. We have a 55 kilogram ice skater who is initially at rest on a flat skating rink, and she requires a 198 Newton horizontal force to be set in motion. However, after the skater's in motion, a horizontal force of 175 newtons keeps her moving at a constant velocity. Find, excuse me, I should have capitalized that F, find the coefficients of static and kinetic friction between the skates and the ice. So let's write down our two equations for the coefficients of friction so we can remember what it is those look like. Remember, the coefficient of static friction is equal to the maximum static friction force divided by the normal force. And the coefficient of kinetic friction is equal to the kinetic force of kinetic friction divided by the normal force. Next, let's write down what we know. We know that the maximum force of static friction is equal to 198 newtons, and that is because the skater requires 198 newtons horizontal force to be set in motion. We also know that her mass is equal to 55 kilograms. So it's obvious we need to find the normal force. In order to find the normal force, we're going to multiply mass times gravity, which is going to be equal to 55 kilograms times 9.81 meters per second squared, and that's going to be 540 newtons. So now we can, we also know the force of kinetic friction. That is equal to 175 newtons, because we recall in our problem that it takes 175 newtons to keep her moving at a constant velocity. So now we are ready to plug these values in and find our coefficients of friction. We know the coefficient of static friction is going to be equal to the maximum force of static friction, 198 newtons, divided by the normal force, which is 540 newtons. And when we divide those numbers, we get a coefficient of static friction of 0.37. Notice that the newtons cancel out, the units cancel out, so coefficients of friction are unitless. Now let's find the coefficient of kinetic friction. So we're going to take the coefficient of kinetic friction, which is 175 newtons, and divide that by the normal force, which is 540 newtons. And we get 0.32 for the coefficient of kinetic friction. And we can ask ourselves, does this make sense? Yes, it takes, the coefficient of kinetic friction is going to be less than the coefficient of static friction because it takes less force to keep her in motion than to initially overcome the maximum force of maximum static friction. So one more type of friction that we're going to talk about before we're done with the video here is air resistance. Air resistance is a form of friction. Usually it is written capital F for the force and a subscript capital R. In this case is referring to air resistance. It's important to remember that whenever an object moves through a fluid medium like air or water, that medium provides some resistance to the object's motion. And through air, this is how we designate air resistance. Air resistance is always going to act in the opposite direction to the motion of the object. For example, the air resistance acting on a moving car acts in opposite direction to the motion of the car. When the object increases their speed, the force of air resistance is going to increase as well. So the force of the air resistance is proportional to the speed of the object. When we look at the example of an object falling through the air, like this skydiver here, as that free-falling object accelerates, its velocity will be increasing. And obviously, as the velocity increases, the air resistance also will be continuing to increase. When the upward force of the air resistance equals the downward force of gravity, we have what we call terminal speed, or sometimes it's called terminal velocity. At this point, the net force on our object is 0, and the object continues to move downward with a constant speed. It does not continue to accelerate. So that is what terminal speed or terminal velocity is. So quick review, we talked about friction, static friction and kinetic friction, and how those are related, and the friction on a microscopic level, friction and the normal force, and that those are proportional to each other. We talked about two different kinds of coefficients of friction, coefficient of static friction, coefficient of kinetic friction, and how to calculate those. Here are a couple extra advanced ideas if you want to do some advanced proficiency. If you are interested in some more difficult problems, there's problem 1 on page 147 in your textbook, section 4D. You will definitely need to look at some of the example in the book, probably to do that problem, but if not, good for you. And I look forward to seeing you in class and seeing what you have to come up with.